So, hello everyone. Hello everyone. Welcome to today's live interactive session on geology and soil mechanics. So, as you all know, today will be the last discussion session for this course, and we have already covered the course. Just today, we will be just recapitulating whatever you have studied in these 12 weeks. We'll just going through all of the, we'll just go through all of the stuff that we had discussed, the problems that we had solved. Okay, so we're just going through all of those very fast. We'll just skim over those topics, and if you have any doubts or queries, you're always welcome to stop me and ask me any questions. And yeah, so your exams are nearing. Those who are appearing, those who will be appearing for your exams, all the best to you. And if you have any doubts, please feel free to contact me anytime, even after the class. Please feel free to write to me. You can mail me anytime. I will be more than happy to help you out. So let us start the session. I will start just skimming from the uh, first uh, week, and then we'll be ending with the 12th week. Okay, so yeah, so let's start. Yeah. So in the first week, we actually started our discussion of this course with what are soil and what soil, how soils are actually formed, how soil is actually formed, right? So we know the soil is actually formed from rocks. There are various types of rock, igneous, sedimentary, metamorphic rocks, and due to weathering, chemical and mechanical weathering, and yeah, due to various other events, what happens? The soil rock disintegrates, and from that, soils are formed. Also, one more thing that we have to notice here that if the soil is there present uh, at the location where the rock is integrated, that is the residual soil, or you can have the soil can be transported from one place on the earth surface to another place through a river, through water bodies, through air, wind. So that will be called as transported soil, right? So this is how basically this was the basic thing that we discussed. And the main technical, first technical thing that we discussed was soil as a three-phase system, isn't it? So we defined the soil as a three-phase system where the three phases are our air, water, and solids. So this forms the main soil mass, right? So we have the soil particles, the part of solid particles, then we have the water, and then you have the air. So we can have, if all the voids in the soil are covered with or filled with water, we will call it a completely saturated soil. And if the voids are empty, that is, it only has air in it, we'll call it a dry soil. Right, so then we define the weight of water, weight of solids, all these things, and all the volumes we defined. And based on that we define some properties known as the index properties. So what are index properties? Index properties are nothing but these are there are some tests that we do to classify soil. Those are known as classification tests. And from those tests, whatever numerical results that we obtain, that are known as the index property. Okay, so there are different types of index properties. So by now you are proficient in these terms, right? You are proficient in these terms. These are nothing but water content. Okay, weight of water by weight of solid time 100%. What percentage water content? Then we have void ratio. After void ratio, we have porosity. Then we have degree of saturation. We have air content. We have percentage air voids. We have bulk unit weight. We have the dry unit weight. We have saturated unit weight, submerged unit weight of solids, specific gravity of solids, grain size, and then we can that. So these are all the basic index properties. After that, we saw what the grain size distribution curve is, right? So what is the grain size distribution curve? So it is nothing but the plot of percentage finer with the size of particles. So how can we obtain the grain size distribution curve? We can obtain the grain size distribution curve from the we can obtain the grain size distribution curve from the uh, sieve analysis, right? So we also saw what sieve analysis is then, right? So we arrange sieve in a particular order, and then we sieve the soil through it, and then measure the proportions of soil that is retained in its sieve, and then from there we can calculate the percentage finer. So that is the dry sieve analysis. So for the fine grained soil, okay, the soil is mainly composed of fine grained soil. It is the soil critical size is less than 0.075 mm, that is 75 microns. Then we have to go for right. Then we have to go for wet sieve analysis. So how do you do wet sieve analysis? Uh, how do you do wet sieve analysis? We do wet sieve analysis using special instrument called hydrometer. Right? We saw that. So how we saw how hydrometer works. Okay, how the hydrometer actually looks like we saw, and then we saw how the hydrometer works, right? And what are the various different corrections, that is the meniscus corrections, okay, the dispersive agent correction, temperature correction, all these things we saw. Then again, we saw some terms known as the D10 size, which is the effective size. Is called that effective size. It is nothing but the size corresponding to the 10% finer. And then you have the CU, that is the coefficient of uniformity, that is nothing but D60 by D10, and it should be greater than 4 for gravels and greater than 6% for the soil to be called as well graded soil. Okay, then you have the coefficient of curvature, which is nothing but D30 squared divided by D60 to D10, and this should be between 1 to 3. So this both these criteria should be satisfied. So to call the soil as a well-graded soil. So well-graded soil means all good equal proportions of all sizes are present. Okay, good proportions of all sizes are present, equal distributions. Then we came across one more important topic known as the consistency of clays, right? So, what do you mean by consistency of clay? Consistency of clay is nothing but the degree of firmness. Okay, the degree of firmness of a clay is known as the consistency of clay. For to define the consistency of clay, we define certain limits known as the Atterberg limits. So Atterberg limits, you can see here, we have the volume versus water content plotted here. Okay, so initially the volume is constant. As you keep on increasing the water content more in the soil, the slope remains same and the volume rises like that. Okay, linearly. So the water content above which the soil does not have any strength and it behaves as a liquid is known as the liquid limit. Between if the water content lesser than between the plastic limit and the liquid limit, the soil will behave as a plastic substance. That is, it can be molded. Okay, so potters usually work in this region. Potters, they mold the clay. You have seen they mold clays to make various nice looking objects with clay. So they operate in this region. Okay, they keep the soil plastic. Then if we further reduce the water content, we will get a semi-solid soil. All right, semi-solid soil, and then we further reduce the water content below this limit WS. This is nothing but the shrinkage limit. So below shrinkage limit, there is no more change in volume. So from shrinkage limit to the point where there is no water in the soil, that is dry soil, the volume remains constant. Okay, the volume remains constant. So from shrinkage limit to dry soil, at shrinkage limit, whatever volume the soil will have, same volume the soil will have when the soil is dry. Okay, so this is a very interesting property. Then how to determine this liquid limit and plastic limit, that we also saw a little bit. So we have the liquid limit test, Akasaka apparatus that is used. Okay, to determine the liquid limit, then plastic limit we can determine by rolling the soil. Okay, Then what is plasticity index? Plasticity index is nothing but the difference between the liquid limit and the plastic limit of a soil. So zero plastic limit means the soil is non-plastic, less than 7 means low plastic, 7 to 17 is medium plastic, and greater than 17 means highly plastic. Then we have relative density. Relative density is generally defined for coarse-grained soil, that is sand. Okay, relative density generally defined for sand, coarse-grained soil. So it shows how densely packed the sand or the coarse-grained soil is. So relative density is defined as E max minus E natural divided by E max minus E mean. Okay, E max is the void ratio in the loosest state, and E mean is the void ratio of the soil in the densest state. Then we solve some problems regarding this uh, index properties. So there are some volumes were given, and we were asked to find out some index properties like the water content and all those stuff. All right. So similarly, we solved some more problems where we calculated water content, and we calculated water content, void ratio, porosity, all those stuff we calculated, density, total unit weight, saturated unit weight. Okay, then we saw if two type of soils is mixed, then what will be the void ratio with hard soil? Okay, those kind of problems we also solved, right? So these are interesting problem. You should know what is the concept behind this. So volume of soil solids always gets added up. Okay, so the thing that's added up is the volume of soil solids. So that you know, from there you can find the volume of void. Since you know the total volume, then you can finally find out the porosity or void ratio, whatever is required. Really, we solve some more problems, similar problems. Okay, so we found out natural moisture content, dry unit weight, similar problems, right? Okay. So what is this? Similar problem, huh? So see this problem is a little bit what to say, not difficult, but you need to put some logic behind it. So we see this problem properly, yeah? Then we saw this borrow pit embankment problem. So we have a borrow pit from where we are bringing a soil and dumping to form a to make an embankment into a site. So in that case, how the mathematics or the calculations work that we solve. So please to have a look into this. I hope you recall how we solved these problems. Okay, so this was a problem related to the determination of liquid limit. So you have number of blows, water content, you plot it, then the corresponding to 25 number of volts, whatever water content is you get, that is nothing but your liquid limit. Okay, so corresponding to 20, so you have the points, so you draw a certain line, approximate line, then corresponding to 25 number of blows, whatever water content you get, that is your liquid limit. And you see that the graph, it is semi-log, right? So here you have log scale, you have a normal natural scale, and here you have a log scale. Then similarly, this is one problem where determining the void ratio and shrinkage limit. Okay, there we use that concept that the void volume is same volume at this point and this point are same. So the void ratio is also same here to here. That concept we used. Okay. Again, one more problem regarding calculation of shrinkage limit, similar problem. That's all. Now, just a now regarding the second week, in the second week, let us see what we did. Yeah. So the second week, it was all about soil classification. So we saw how we classify soil. First, we have to understand what is the purpose of soil classification. Okay, so what is the objective of soil classification? What is the purpose of soil classification? So to group soil which show similar behavior, that is the objective of soil classification. So why do we classify soils? Because it provides us with information about the probable engineering behavior of the soil. So if you know that this, say this is a silty sand, you can estimate what kind of property that soil will actually have. So that's why we want to classify soil so that we can estimate, we can guesstimate actually. The correct word is guesstimate. We can guesstimate the approximate property of that soil. Okay. So there are different types of soil classification system. You have the USCS system. There's nothing but the Unified Soil Classification System. Then you have the ASTO system by American Society of State Highway Transport Official System, ASTO system, and then finally you have the Indian Standard Soil Classification System. So the USCS and the IS we are almost same. There's a little bit different between this how we classify low plastic and high plastic clays. Otherwise, it's completely same. So we looked into the industrial resource classification system that is given by the IS 1498, 1970. So you have some uh, major soil groups that are there that we have initially classified the major groups. So that are nothing but the gravel, sand, silt, clay, organic, and peat. Those are the major groups. So that will generally give us the prefix. So generally we have two parts of soil classification system. You have a prefix and you have a suffix. So the prefix will be formed due to this major soil group. And then we have the subgroup that is nothing but well graded, poorly graded, silty, clayey, low plastic. This will be not uh, uh, low plastic, intermediate plastic, or highly plastic. Okay. So for gravel and sand, these are some of the uh, probable what to say, classic soil classifications that we can have. We have well-graded gravel, poorly graded gravel, silty gravel, clay gravel, well-graded sand, poorly graded sand, silty sand, clay sand. Okay, so these are for the coarse grained soil. Then we have for the fine grained soil, we have low ML, inorganic silt, then CL, OL, MH, CH, and P. So coarse grained soil can be boulder, cobble, gravel, or sand. So if the size is greater than 300 mm, we call it boulder. If it's between 300 and 80 mm, we call it cobble. If it's between 80 mm and 4.75, then we call it gravel. Okay, then you have coarse gravel, fine gravel again. Then lesser than size, smaller than 4.75 mm, but higher than 75 microns, we call it sand. And again of coarse, we define fine sand. And for fine grained components, that is the component having size lesser than 75 microns, we can have silt, clay, and organic matter. Okay, so let us read this. Where a fine fraction in a coarse soil, that is when the percentage of soil passing 0.0, that is 75 micron sieve, is less than 5%, classify on the basis of grain gradation. So when the fine fraction in a coarse soil, so when if more than 50% of a fraction is passing through is size having greater than 75 micron, and the percentage having size smaller than 75 micron is less than 5%, then we classify on the basis of gain in gradation, that is well graded or poorly graded. Okay, and for fine grained soil we classify using the plasticity chart. This is the plasticity chart that we use to classify fine grained soil. Okay, for fine grained soil, for coarse grained soil, we classify in different, and for the fine grained soil, it is different. Okay, so we use this chart for fine grained soil. So if it plots above the chart, it's clay, below the chart, it's silt, and you have this A, this line is called the A line. You have the equation of this A line that is given. Okay, this is the plasticity index, this side is with limit. So when fine fraction in a coarse soil is greater than 12%. So in the fine fraction in a coarse soil, the coil is mostly coarse, but the fine fraction, the amount that is passing to 75 micron is greater than 12%, then we do not classify the coarse soil in terms of grain and gradation. In that times, we classify the coarse soil as clay coarse soil, clay gravel, clay sand, or a silty gravel, silty sand, like that. Okay, just have a look at here. Okay, this highlighted portion. It's an important point. And dual classification is used when we have fine-grained fine fraction in a coarse soil between 5 and 12%, then we have to use dual classification. And these are other possible dual classifications that we can have. Now, steps for classification. First, we do the grid size distribution analysis. Then, we do using the sieve analysis or hydrometer analysis. If greater than 50% is retained on the 75 micron sieve, then the soil is obviously a coarse soil. If greater than 50% retained on 4.75, then it's a gravel. If greater than 50% passes 4.75, then it's sand. Now, if fine fraction in this coarse soil is less than 5%, then the suffixes will be either well graded or poorly graded. And if it's greater than 12% fine fraction, then you have to use clay or silty as the suffix. And 5 to 12% if it's their fine fraction, then you have to use a dual classification. Now, if more than 75, more than 50% of the soil is passing through 75 micron, then the prefix will be either clay or silty, and in the suffix you will have either Li or H, low, intermediate, or high. Okay, then we saw something about the soil structure. So what is soil structure? Mode of arrangement of soil particles plus forces between them that hold together. There is a soil structure. Gravity is the force in coarse grained soil, whereas surface bonding force is the predominant in fine grained soil. What is specific surface? The ratio of surface area of the material to its mass or volume is known as specific surface. For fine grained soil, it is a specific surface is going to be very high because they are small size. So the particles is small, you have a larger specific surface. Which is rather surface area, so hence you will have a large specific surface. The specific surface determines which is dominant gravity or surface tension force. So fine grained soil obviously specific surface is high, so that's why surface bonding forces govern. Clay soil are made up of clay minerals, clear plasticity and cohesion. Clay minerals are electrochemically active. Soil structure mode of yeah, chemical weathering forms clay minerals. Okay. Clay minerals are divided into three groups based on their crystal arrangement: kaolin, montmorillonite, and illite. These minerals are built of two fundamental crystal sheets: tetrahedral sheet and octahedral sheet. Stacking nature of bonding force and metallic ion in the lattice differentiate them. And we have the uh, tetrahedral sheet. Okay, so we have the tetrahedral sheet. You have four oxygen ions at the sides, and in the center you have one silicon ion. It is a tetrahedral sheet, and you have the octahedral sheets. You have six OH minus ions, and in the between you can have Al aluminum or magnesium. It's aluminum. It's called gypsite. Then what is isomorphous substitution? In terminalities, metallic ions may substitute by other metallic ions having lower valence but similar size. So that is known as the isomorphous substitution. So due to this, you can develop a positive or negative charge. Okay. Now, clay minerals we said. So we have kaolin. So in kaolin, you have this gypsite and silicon, this arrangement like this silica sheet and gypsite sheet. And there your hydrogen bond, you have hydrogen bond, which is very strong. As you know, the strongest bond is the hydrogen bond. And that's why this kaolin, clay between kaolin is least active. Okay. And then we have the montmorillonite, these have this kind of arrangement, and in the between you have weak van der Waals bonds. So what happens, it can absorb a lot of water atoms, water in this weak zone, and it can absorb a lot of water, and the clay minerals formed with montmorillonite can swell a lot. Okay, it can expand in volume, it can swell a lot, and hence this type of soil are known as expansive soil. Then you have elite. So what is elite? So in elite, it's similar to monopolar, structure is similar to monopolar, but here you have this potassium ion. It makes the bond a little bit more stable, so it's less reactive than monopolar, less expansive than monopolar. And clay particle interaction in aqueous environment. Clay particles may flocculate or disperse. Flocculation mostly in this H2 phase configuration, and dispersion is like this phase to phase configuration. Okay. Just a second. Yeah. So then we solve some problems where you had the greenhouse distribution data given, and you have to classify the soil. Right, so this is was particularly easy because directly it was given it's a sports soil. So just you have to see that how much was so see more than 60%, more than 75% is passing through 4.75 mm, smaller than 4.75 mm. So it's obviously it's a sand. That's more than 50% is smaller than 4.75 mm. It's definitely a sand. And then we just have to calculate the CUNCs to determine that whether it's a poorly graded or well graded soil. Okay. There is no question of clay here as because none of the fraction is actually smaller than 75 microns. So then similar problems we solved. So let us see the problem also. From the civil data to classify the soil, given that the size of aggregates were linearly and the fine fraction is not non-plastic. So this is similar. So let us not repeat it again. And so these are some problems, similar problems that we solved. Okay, so green size distribution data was given. Okay, percent is fine. Let's calculate CU. We told that whether the soil is well graded, poorly graded. Okay, so it's better I do not go to the problems one by one because we have already solved the problems, right? So yeah, if I see some difficult problem, then I will tell. Otherwise, let us not. Okay, so these were just simple basic problems, right? So there is nothing much. So this one you can see that here the plasticity index. So this was one important problem. So classify soil. If it has a following properties, percent passing 4.75 mm is 98%, percent passing 75 micron is 35%. So 4 point. So definitely we have to classify it as a coarse soil because less than 50% is less than 50% is passing through 75 parts micron sieve and more than 50% is passing through 4.75. So it's definitely sand. Now the question is that what will be this prefix is sand, right? So what will be the suffix? So for the suffix, you have to see that greater than 12% is passing through 75 microns. So you have to classify it based on the fine fraction, so either clay or silt. Now, these things, these 60 these are actually given to confuse me in the question. Okay, actually, I do not need them. So, what is the plasticity index of the soil? It's 3%. So, 3% it falls between 4 and 7. So it is a typical case where you have to use dual classification where CLML this and we use this. So we have to classify this as SCSN because you cannot definitely say whether it is a clay or it is a silt. Okay, because it's come in this part. Okay, but this one I think it's 3%, right? So liquid limit is 3. Liquid limit is 22, right? So here. Actually, the thing is, it does not not 4 to 7%, but you see the plasticity index is 3. That means my it's around here. It's just touching this line, okay. And now the liquid limit is 22%. Means here, so it's plotting here. So it can be either SM. You can write it either as SM or SCSM. Okay, because it's just very close to this part. That's why it's better that you use a dual classification. Okay, even if you write SM, it's correct. Even if you write SCSM, it's correct. Okay, that's the thing. Because it's falling very close to this part. Because of this one, I would determine the base exchange capacity of a clay if 100 gram of dry clay soil adsorbs 80 milligram of calcium. Find the quantity of hydrogen that can be adsorbed by 5 millimeter of this clay if the dry unit weight of clay is 1500 kg per meter cube. Okay, so what is base exchange capacity? Base exchange capacity is the ability of clay particles to absorb ions on a surface or edge. Now, 1 milli equivalent is equal to 1 milligram of H plus. 1 milligram of milli equivalent is 1 milligram of H plus is nothing but 40 by 2 milligram of Ca2 plus, because Ca2 plus is 2 ions, so 20 milligram will be sufficient for 1 milli equivalent, right? So 20 gram of Ca2. A 100 gram clay has 80 milligram of Ca2 plus, which is nothing but 4 milli equivalent, that is nothing but 4 milligram of H plus, you can write like that, right? Now 100 gram has 4 milligram of H, 1 kg will have this much, so you have to find out 7,500 will have how much amount of H. Why 7,500? Because you can see that it is given 5 cubic meters times 1,500 is the density. From there you get 7,500 kg. So for 7,500 kg, 0.3 kilogram of hydrogen is required in that shortage. Yeah, so let's do this. Just give me a moment. We'll start this. So what is soil compaction? Soil compaction is nothing but to densification of the soil is known as soil compaction. So we apply some mechanical, external mechanical energy, okay, or compactive effort to densify the soil, and that is known as soil compaction. So what is needed in construction of highway, embankment, dams, etc. We need to determine the number of passes of roller and the quantity of water to be mixed. What is compaction? Densification of soil by the removal of air. This process requires some mechanical energy. Water added to the soil during the compaction acts as a lubricant. This helps the soil particles to come closer to each other and obtain a better packing. But beyond a certain point, the water starts replacing the soil particles that occupy the space. This increases the diameter. So initially, as we increase water, the dry density increases because the water has some lubricating effect. And then as we keep on adding more and more water, what happens? The water actually reduces the soil particles in that particular volume, and so the dry density reduces. The moisture content at which the maximum dry unit weight is obtained is called the optimum moisture content. Okay, so this point where you have the maximum dry density is known as the oh optimum moisture content. Okay, optimum moisture content. All right. The standard Proctor test is going to determine the OMC. So what is standard Proctor test? So these sizes are not the standard sizes. In the standard sizes are somewhat different. So please look at the standard in the standard codes for the in the standard size. What size of mold you use? What size of die you use? Please have a look at that. Okay. So in standard Proctor test, we have 944 cc. Dia, we have this number of flows. You have 25 number of flows for each layer of soil that we put in this mold, and you have to put total 3 layers. And the hammer weight is 2.5, and the height of fall of this hammer in this channel is 30.5 centimeter. So find moist unit weight from the volume of mold and weight of soil. Okay, so moist unit weight is nothing but moist weight by volume of mold. Then calculate dry unit weight. It is the volume of water content. So you need to measure the water content of the soil. So dry unit weight is moist by 1 plus water content. For a given moisture content and degree of saturation, the dry unit weight can be represented as gamma D is equal to G gamma W 1 plus E. Right? So you all know these expressions quite well. Right? From our first class. Then also we see equal to W into G. So gamma D can be given as G gamma W plus WG by S. Now for full compaction, there should not be any void present. That is, air void should be zero. In that case, only soil, solids, and water should be present. That is, if all the air voids are expelled, the volume reduces, and in this reduced volume, the soil is 100% saturated. It is S equal to 1. Right, so let's remove, and with this volume you have now. Okay, and this volume, the what soil is 100% saturated. In that reduced volume, soil is 100% saturated. That is S equal to 1. Hence, the maximum dry unit weight that is theoretically possible at a given water content is when there are zero air voids. That is, we have S equal to 1. Okay, then we have the you get a line. This is the zero air void line. This is a theoretical maximum dry density. Okay, when you put S equal to 1, you have considered AB zero air void. Okay, so that is known as the zero air void line. So if you plot it, you will get one line, you will get the zero air void line. So these are the actual, the maximum, theoretical maximum dry unit weights that you can get at any particular of moisture content that you can get from the zero air void line. There are various factors that affect compaction. Right, so there are various factors that affect compaction. Uh, we have the grain size distribution, shape of soil grains, type of clay, all those things. It affects the compaction. Then you have the compactive effort. So if you increase the compactive effort, your this curve shifts to the left and up. Okay, left and up it shifts. Okay. So if you turn all these lines, optimum lines, you can get a line of optimums. But these are always away from the zero air void line. You can never attain this theoretical maximum value. It is nothing but a zero air void line. It is the modified product test where we have higher number of layers and higher weight of hammer and higher fall of hammer. Okay, so higher compactive energy you're putting. Okay, then standard Proctor test you're putting a higher amount of energy in a modified Proctor test. Okay. See. Just a minute. Okay, so then we have different types of field. How can we achieve the compaction in the field? So we have different types of rollers. Smith wheel roller, pneumatic rubber roller, ship's foot roller. So yeah, the ship's foot roller generally is for clay soil, vibratory roller generally for sandy soil, all those stuff. 90 to 95% of the maximum density determined in the lab is actually implemented in the field. It is, we determine that by a term called the relative compaction. So maximum density to be achieved in the field for the maximum density in the lab times 100%. Okay. Determination of field unit weight, sand cone method, double barrel method, nuclear method. So yeah, the sand cone method. So I'm not going into depth. So you already know, already discussed in it, right? So how to do the sand cone method, and I suggested that you watch this video where properly this is given. So should we watch the video? You can watch the video. So you can watch this video. Okay. Nicely, they have shown uh, how how this sand cone method can actually be used. Okay. All right. So then we have the next topic is permeability. So what is permeability? Water flows through soil with the presence of interconnected voids Flow occurs from point with higher head to lower head, obviously from higher energy to lower energy. Some head loss occurs in this process, right? So the property by which the soil allows water or any other fluid to pass through it is known as the permeability. Right, so you have a hydraulic gradient. We define hydraulic gradient. Hydraulic gradient is nothing but the head loss divided by the length of flow. Then the velocity of flow in the soil pores, the pores in the soil network is very small, right? So we can consider that the flow is laminar. So laminar flow means that there are no interaction. There means there is no interaction between the different layers of fluid that are flowing. Okay, so laminar. So the smoothly the layers of fluid are flowing. Okay. So in that case, what happens? The velocity of flow is directly proportional to the hydraulic gradient I. Okay, beginning laminar flow. So V is proportional to I. So then we can put it. Then you can introduce a uh, proportionality constant, which is nothing but K, which is nothing but the coefficient of permeability. Okay. Then you have what is seepage velocity? The seepage velocity and so what is seepage velocity? Seepage velocity is the actual velocity of the flow of fluid through the pores. Okay, and this seepage velocity is always greater than the discharge velocity. Okay, that is the velocity that we get by considering the total complete area of the soil. And seepage velocity is when we uh, consider only the this uh, area of the pore network. Okay. So what are the factors affecting central conductivity or permeability? So you have the fluid viscosity, temperature, pore size distribution, thickness distribution, void ratio, roughness. And see, actually, we have. I'm not discussing again how each of these property, each of these quantities actually affect hydraulic conductivity. But see in your textbooks properly how each of these actually increase or reduce the hydraulic conductivity. Okay. Then we consider that we start solving some problems. Okay. This is nothing but the number of passes, calculation of the number of passes that is required in the field. So you need to calculate how many number of roller passes that we have to ensure for that amount of proper compaction. Okay, that calculation we did here. Then we had some results from our ice light compaction. This light compaction test. Industrial light compaction test. So industrial light compaction, from there we calculated these quantities and then we plotted this dry density versus water content, and from there we can find out the pure moisture content. Okay, all those things we did. Yeah, let's see. Yeah, all those things are easy only. Okay, so see this problem little bit properly. This borrow fit problem again. Okay, it's easy, but let's see it once. Yeah, then this is a easy problem from this variability. So you have the head difference, you have the soil length that it is passing. So you need to calculate the hydraulic conductivity or permeability. So it's visible to I, Ki. the flow is nothing but velocity into area. Velocity is ki, so q is kia. From there, you know the q. If you measure the q, you know the I is this 15 minus 5, 10 by 12. That is the length of flow, 10 by 12. I will give you I. Area is 8 centimeters square. It's given. From there, you can calculate the ideal conductivity. Similarly, one more problem, same problem. Okay. Here we also calculate the seepage velocity. So you can get the porosity, we divide the porosity by the discharge velocity, we got the seepage velocity. Okay, so then this problem is solved, where we made one table, elevation head, pressure head, total head, and head loss. From there, we calculated the heads at all these points. Okay, all various points. So main target was to find at the point A, but during the calculation, we calculated all the points. Okay, so see this kind of problems properly. These are very nice problems. And next is this. Let's continue. So yeah, so how to determine hydraulic conductivity in the laboratory? So we have two kinds of tests: constant head test and the flowing head test. So in constant head test, you actually keep the head of water constant throughout the test, and in flowing head test, the head of water actually reduces as the test progresses. So granular soil, as you know, it will obviously have higher hydraulic conductivity, right? It will have higher hydraulic conductivity, and hence it's better that we use the concentrate test just to have a check to the higher volume doesn't pass. So higher volume, very high volume of water does not pass. And then we have the fine grained soil. Fine grained soil, you know, as will be having lesser hydraulic conductivity, so it's better that we use the falling, not flowing head, it's falling head test. Okay, so it should be falling head test, not flowing, or it generally it's called falling head test. This is better. Okay. Then yeah. So in falling head test, you know the head that is maintained throughout the test. You know the area of flow. Okay, so in a certain amount of time, certain volume of water will pass through the soil and get collected in this graduated flask. So then you can measure this. That is nothing but capital Q. So if you get no capital Q, you divide by the area of flow, this area of cross section of the soil, times I, that is the hydraulic gradient, times the time required for that amount of water to get accumulated in the jar. Then you can find out the K. K is nothing but the uh, hydraulic conductivity. Okay. So K I you can replace H by T. So K can become QL AHT. Okay. Then you have the falling head test. So falling head test, what happens? We have the standpipes here, right? So the head will fall throughout the test. Okay. So initially it will be H1, then it will be H2 up after time T. Initially at time T1, say it's H1. At time T2, it will be H2. Okay. And at any time, we can say the head is H. Okay, and DH is this infinite symbol small height here in the standpipes. So then you can write that Q is equal to KIA, KLAHT is equal to the Q, you can write minus A dH by dt. Okay, Okay, minus AdH by dt. Then you can just put rearrange the terms and then integrate, and then you can find K is equal to ALAT ln of H1 by H2, where small a is the area of the standpipe. Okay, A is the capital A is the area of cross section of this sample. T is the time required for the head to drop from H1 to H2, that is nothing but T2 minus T1, and H1 which we already know heads. Okay. Now there are other some empirical relations also of the hydraulic conductivity to theta and size of these that we discussed in briefly. These are nothing important. Okay, so then we calculated this horizontal flow and vertical flow. Okay, equivalent horizontal flow and vertical flow. Okay, so there are those things we did. So for equivalent horizontal flow in all these layers having K1, K2, K3 up to Kn hydraulic conductivity and different thicknesses H1, H2 up to Hn, and the flow is horizontal. Okay, the flow is horizontally, the flow is there. In that case, so what is the equivalent hydraulic gradient that we calculated? Then we have a vertical flow in the case where the water is flowing in this direction. Okay, it's actually flowing in this direction like this vertically. In that case, what's the thing that we calculated? In that case, the equivalent hydrogen conductivity is given by this expression. Okay, so in the site, we can calculate the hydraulic conductivity that can be done using this pumping of water. So we have main test one test well, and then we have two observation wells that we draw that we pour into the soil, and you have one test well. Then you start pumping out the water from this test well. Okay, you start pumping out the water till the water that is coming out that attains a particular rate. Okay, constant rate. You keep on pumping out. Then what you do, then you measure at, so you know that these distances at which these two observation wells are there, so you measure those distances, then you measure the depth of drawdown. Okay, so a depth from the original level of water table, what is the depth that the water table is receded now? Okay, so initially the water table was here, but as you are pumping out, obviously it is going to draw down, and obviously the water table will recede. Okay, recede. So you need to measure these drawdowns. Okay, then we can use this expression to calculate the hydrostatic conductivity. Okay, then what is seepage? Seepage is nothing but the that nothing but the flow of water. Okay, flow of water uh, through the soil. So how can we actually mathematically define the flow of water in a porous media like soil? That is given by this seepage theory. Okay, so in seepage you can see we have dou v by dou x plus dou v z by dou z is equal to 0, is nothing but the uh, what to say. So you can see what the quantity of water entering here is equal to exiting here, entering here. This one is exiting here. So whatever is entering, so there we consider that when there is CP, there is no volume change because it is well perfectly saturated. There is no not saturated, there is no volume change. So don't have any source term on the right hand side of the direction. From there, we can get this equation, which is known as the Laplace equation, is equals to 0. Okay, so kx is the hydraulic conductivity in the x direction, kz is hydraulic conductivity in the z direction, and so on. So we get this equation and the solution. And for isotropic soil, where in both x and y direction, x and z directions, there are same hydraulic conductivity. We can have this equation. Okay. Okay. So h square to h is nothing but the head. Okay. So h square by the x square plus h square by the z square equal to 0. We're considering that the soil is saturated. Okay. Okay. Yeah, so the solution of this Laplace equation is a family of curves. Okay, is a family of curves, two sets of curves. One are known as the equipotential line, and other set of curves are known as the flow line. So these family of curves are nothing but the solution of this Laplace equation, and these lines actually define how the water or how water is going to, or how a uh, liquid is going to flow through the soil network. It's going to flow through the soil. So this family of curves that are the solution of this Laplace equation are nothing but the equipotential lines and the flow lines. And these equipotential and flow lines actually define how water is going to flow through the soil, or water is going to seep through the soil. All right, so the solution to the continuity equation is the Laplace equation of flow lines and equipotential lines. These lines are orthogonal to each other. So always these lines are perpendicular to each other. They form a family of curves, and so you have pairs of flow lines, you have pair of equipotential lines, and these elements that they make, these are almost generally square. Okay, and this network that they form, this family of curves, these are known as the flow net. Okay, the flow net. Okay, so the space between two flow lines is known as the flow channels. Okay, space between two flow lines is known as the flow channels, and these equipotential lines are the lines where along the line, at all points in each line, the head is same. Okay, that's why it's known as the equipotential lines. At all points of the line, on one line, at all points on one line, the head is same. That's why it's known as the equipotential line. Okay, these are the equipotential line. This. Okay, this inverted U shape is equipotential line, and U shaped ones are the flow lines, and inverted U shaped ones are the equipotential. And we saw that how can we calculate the seepage using flow net is nothing but flow is KH and F by ND, where NF is the number of flow channels. Number of flow channels, that is the number of channels formed by two flow lines, is known as flow channels, and ND is the equipotential drop. Then see, so we have a certified soil here. We're asked to equate the effective permeability in horizontal and vertical direction. So we have different thicknesses of soil. We have different permeability of each layer. We calculated the horizontal flow, what will be the effective permeability, and then we have for vertical flow, what will be the effective permeability. So you can see here that the horizontal effective permeability is always greater than the vertical effective permeability. Okay, so this is always true, right? This is always true. So these are all similar things that we so here the flow seems to be horizontal, but it's actually the vertical flow problem, right? Because the head drop here is different than here, than different here, and the flow will be equal. Entering this is equal to entering this and entering this. So it's nothing but a vertical thing. It looks horizontal, but the flow here is the case is the vertical flow case actually. You have to use this expression if you want to determine that. We did, we found it out. So that's all. Yeah, we solved some problem regarding this permeability test, Polynet test, and concentrate test. Some problems. Uh, then some problems from this aquifer or this test well problem. Yeah, these problems we solved. Solved a lot of problems actually. And this problem that was left in the previous class, that also we summarized. So as I said, what are flow nets? So how to draw flow nets? So several trials and error are directed by flow net. So here you can see A, B, and D are equipotential lines. So the flow lines intersect them at right angles. FG. Yeah, okay, see in this. FG is a flow line. FCT is a flow line. Okay, FG means this. This is a flow line. Then ACT. This is a flow line here, but and this is equipotential line. This is equipotential line. These are equipotential lines. Equipotential lines intersect FG and ACT at right angles. So here you can have these are right angles. These are right angles. Okay. Flow channel is a strip between and equidistant flow lines. So discussed. This we already discussed. Okay, H and F I N D. This thing already also we discussed. Now in anisotropic soil where you have different Kx and Kz, how we can do that, how we can draw the flow lines, that is also shown here. So I have the vertical scale for drawing the flow net, choose the horizontal scale such that horizontal scale is and the vertical scale, construct the flow net as particular procedure. Uh, then you have the rate seepage, you can calculate by this expression. Then how to determine uplift under a hydraulic pressure. So okay, if you have hydraulic structure, there's a dam, you can see that there will be some seepage flow like this, right? Underneath. So underneath the seepage flow, there will be some upward pressure that the soil via that the water flowing water might create. So how can we calculate that uplift pressure? That also you can, so that we can also calculate using these flow lines, flow net. Okay. Just a second. Let's see one thing. This one I think should be into horizontals. This one you should check. Okay, once please check this particular point. You just this particular point to check this with some good books. Okay, some good soil mechanics book to check this, or check from the internet ones. Okay, this I'm unsure. This should be what this thing. I'm unsure of this thing. We just check this one, sir. Just a second. Let's check. See if we get some videos or something. There are some videos also available on the internet. I think these things. Okay, so what I'll do is I will share this video link. Let me just share this link. The link with you. There is a good video that I could find out. Mm. Got it. Mm. Mm. The link. Should I paste it? Yeah. Okay, so have a look at this video. Okay, this here they have. I think they have done it correctly. Okay. This is, I think, not correct. I think not correct to see some books yourself. See, it should be scale. So I think this is not right. Just see this video once. Check this video once. Okay, then we have seepage through earth dams. How we can do so? To peat solution we have, right? if all these solutions that are Rasagande solution, all those solutions that are there, they actually gave, yeah, expressions using which we can calculate the seepage through RTEMs. Okay, so KL10 alpha sin alpha, so alpha you can get from your RTEM geometry, you know. Right then, certain alpha sin alpha you got. K, you know, for the soil, L you have to find out using this particular expression, then you can get the seepage flow that is happening. Okay, so these are the various steps. Now, what are in situ stress? So here we defined the topic of your, we defined what effective stress is, what total stress is, what is pore water pressure, neutral stress, all these things we define. Right. So total stress is nothing but the uh, total load, that is whatever coming into the soil, right? That is nothing but total stress. Now, if it is effective stress is the actual stress that is getting transferred between the soil particles. So total stress minus the pore water pressure, the pore network in the soil will have some pore fluid, so it will exert some outward pressure, right? So if we deduct that the amount of load that is taken by the pore water, we deduct that from the uh, total stress, we will get the effective stress. Okay, so that all those things we did. So, okay, so total stress is effective stress plus pore water pressure. So, effective stress is total stress minus pore water pressure. Effective stress is very important because that is the actual stress that is transferred to the soil, contact to contact. Okay, the granular contact to contact. So, some amount of the stress is taken by soil, soil is under contact, another portion is carried by the water. Some of the vertical component of the contact forces of the soil is divided by the cross-section area of the soil mass gives the effective stress. So this is how we get the effective stress, and then we derive the effective stress like this. Then we saw all these things already. You know how to calculate the effective stress at any point in a so stratified soil layer. We solved many problems. We already know how to do that. Okay, so in upward seepage, what happens? The effective stress actually reduces, and by I Z omega W, gamma W, and in downward seepage, this actually increases. The effective stress at any that actually increases by I Z gamma W. So this the concept is also very important. So if there is upward flow, then effective stress reduces. If there is downward flow of water, then effective stress actually downward flow, then effective stress increases. Upward flow, the effective stress reduces. It's against the gravity. If there is flow of water, then effective stress reduces. And if there is but to say there is downward seepage, then the effective stress increases. When there is upward seepage, effective stress reduces. At critical hydraulic gradient, effective stress is zero. At this stage, there is no contact between the soil. Rain's critical hydraulic gradient is nothing but submerged unit weight divided by the unit weight of water. It mostly between 0.9 to 1. So effective stress is what? Z into gamma submerged minus I Z gamma W, it is equal to 0. From there, you can get critical weight as critical gradient as G minus 1 by 1 plus C. So generally for soil, it's 0.9 to 1.1. Okay, so this is due to seepage. Okay, so when there is no seepage, you don't have that term. You can see there is that term is absent, but term comes from the seepage. Okay, the movement of the flow of water, this term comes. I said uh, gamma W. Okay, so seepage force is I Z gamma W into A. Seepage for part of the volume is I into gamma W. we can get the hydraulic gradient from the flow to nearby the seepage or sinking point. Factor of safety against heave can be calculated. Factor of safety against heave for sheet pipe. Like all those things you see in the book. I'm not going to repeat it again. Okay. Wire filters used in the downstream of any dam or whatever, that also you see. Okay, I'm not repeating. Then we solve some problems to calculate the effective stresses and total stresses and potential pressures at various points in a stratified soil layer. Okay, stuff, nothing complicated. So from here you can calculate the uplift forces at all these points, right? So we calculate uplift forces. Pressure head times the gamma W will give me the uplift force. And what is pressure head? Total head minus the elevation head. The total head is what? Pressure head plus elevation head. Total is pressure head plus pressure head is total head minus elevation. So, okay, then capillary rise, all these things we saw. These are very simple, nothing about. Now then we started consolidation. So what is consolidation? So consolidation is the change in volume of soil, change in volume of soil. Okay, in the saturated soil mass, when we apply some, when the effective stress increases, what happens? The saturated soil mass, you increase the effective stress, so water will drain out from the soil, and due to that, what happens? There is some volume change in the soil. So that volume change, into that volume change, there is some settlement in the soil, and that is known as the consolidation. Okay. So elastic settlement occurs immediately after the application of loads, but this consolidation settlement takes time. Okay. The elastic settlement occurs immediately when there is an increasing stretch in a saturated clay layer. The hydraulic conductivity of the clay is very small. Water takes long time to come out of the pores. The excess pore water generated due to the increasing stress takes time to dissipate. This dissipation is accompanied by change in volume of soil, and this is known as consolidation. Okay, consolidation continues for a long time after immediate settlement. So we use a spring cylinder model to explain the consolidation process. So we are not doing it again. Yeah. So you have this one deconsolidation test from which you can get this word ratio versus log of effect versus log of effective stress curve. Okay, from the consolidation tests. Okay, so you can see, you can get from one deconsolidation, you can get, so you have time, you have deformation. So for each load, okay, for each loading, so you increase our load, such as first you put 50 kg. So 50 kg one load, you can get this, then you get 100 kg. For 100 kg, you will get another curve like this. So for each load from the one deconsolidation test, for each load increment, you can get a curve like this. Okay, with time and deformation you can get. Secondary consolidation, so initial compression caused by preloading, then you have primary consolidation, then you have the secondary consolidation here, that is the plastic readjustment. Okay, so yeah. So how to get this word ratio pressure plots, these all things this is we discussed. I'm not going to repeat it again and again. So we have two methods. We have the this uh, what to say, this height method, calculation of height of solids method, then you have the change in void ratio method. Okay, so you have these two methods using which you can calculate the void ratio at each load increment from the your consolidation test. test. So what normally consolidated soil over consolidated soil, normally consolidated. By now you already know what is normally consolidated soil, over consolidated soil. Over consolidated means that the soil is encountered a higher stress at later, but now that higher stress is released and now is the soil is under a lower stress. So you have a over consolidation ratio greater than 1. So max applied stress in the past, 5% applied effective stress. So by previously in the past history, highest soil was under higher stress, but now it is under lower stress. So you have your cell greater than 1, and this type of soil is the over consolidated soil. Normally consolidated soil means the uh, present applied stress is actually uh, higher than the past applied stress, or actually equal to the past applied stress. So that is the normally consolidated. And there are various terms. So AV is the coefficient of compressibility. That is nothing but the ratio of the E versus effective stress void ratio versus effective stress curve. That is nothing but coefficient of compressibility. Okay, then you have the compression index is nothing but a void ratio versus log of a ratio of the slope of the void ratio versus log of effective stress curve. With the compression index, then you have the coefficient of volume change, and B, then you have the swelling index. Okay, swelling index, that is the swelling curve, then you have the recompression index, this is the recompression curve in the E versus log of effective stress space. The coefficient of compression index, coefficient of volume change, swelling index, and compression index. So main you have to remember here is CC, compression index, coefficient of compressibility AV, and MV, coefficient of volume change. These three you have to remember only. Okay. So this is the basic how the so initially, so say the soil was initially loaded to this part. So this is the pre-consolidation test. So from the here to here, it will have a like this curvature. Then as you cross the pre have a steeper line, that is because the soil is now encountering new higher stresses. Okay, so then you reload it, it will leave it, and then unload it, then again reload it like this. Okay, then we solve some all this some basic problems. That's all. From our consolidation test, we solve a lot of problems. See these problems properly. Okay, how you can get from low bottom to top you go, and you calculate the void ratios. Just see this properly. So, yeah, some more problem where you have to calculate the coefficient of compressibility, compression index, coefficient of volume compressibility, all those stuffs, everything was given. Just put the values and you calculated this. This is where this settlement calculation. Okay. So all those things, yeah. So a clay layer. So yeah, so generally calculate the center of the clay layer, we calculate the effective stresses, and then we calculate the settlement. Okay, so that we did because you want the average settlement, right? So we calculate the effective stresses at the center, and at that center depth only we calculate the settlement. We do this calculation. Okay. So you can also divide it into many layers, and then at the center of each layer you can calculate the settlement. And you can write a simple computer code where you can calculate, you can put the distance tolerance. So you can calculate the optimal number of layers required to accurately calculate the settlement. So see, for one layer, okay, this is one layer. At the center you are calculating, we are getting settlement of 46.3 centimeter. Now what you can do, divide into two layers. Two layers, and at the center of these two layers you calculate settlement. Whatever is settlement. Then you see how much change you are getting. Then you make it three layers. Then you calculate. So like this you can try once. Okay. Well, center means what? That's the average effective stress you are taking, right? Of the whole layer. Then you can make it more accurate by making it two layers, more accurate by making it three layers. Okay, like this you can do. Similar problems. Yeah. Here also same problem. Here also see here one layer of 3 meter at the center of the center of that this clear layer you have calculated. So why not you divide this layer into 1 meter, 1 meter, 1 meter, three layers, and then the at the center of each of these layers you calculate the settlements, and then you add it up. Then you will get one settlement. Now check how much the settlement is varying from the settlement that you calculated from here. That is these things you can check. Understood, right? So you divide this layer into three layers and calculate a settlement at the center of those three layers. Like calculate the effective stresses at the center of those layers and then use that to calculate the settlement. And add those settlements and see how different you are getting from this value. Yeah, yeah, these things you can do. Okay. Okay, so we have very less time. Let's see the next what we have. Yeah, this we already saw. These things we saw. So how to determine this pre-consolidation pressure from this void ratio versus effective pressure plot? This was also discussed, as you can see it's given here. Okay. Then the settlements, how to calculate this, you know. Yeah. Then comes Terzagh is one-dimensional consolidation theory. So this Terzagh is one-dimensional consolidation theory actually helps us to calculate what amount of settlement or what degree of settlement a clay layer will undergo in certain amount of times, certain amount. So what, how much time will it be needed for a clay layer to undergo, say, 50% of the ultimate settlement? So this thing, how can we know? This thing we can know from the using the Terzaghi's one-dimensional consolidation theory. So Terzaghi's one-dimensional consolidation theory actually enables us. Terzaghi's one-dimensional consolidation theory enables us to do this calculation. Okay, to find this out. Okay, to calculate how much time will it be required to achieve a certain amount of consolidation settlement. Okay, so this is the standard one-dimensional consolidation equation that you have to. It's very important. So by dot equal to CV dot square u by dot square. Okay, one-dimensional because we are considering the flow of water, the drainage of water only in the vertical direction, only one direction. Okay, the water is draining only in the vertical direction. That's why one-dimensional. Okay. So then we have time factor. Time factor actually is directly related to the degree of consolidation. That is how much consolidation has happened. It is directly related. It's also related to the how much time is required to achieve that degree of settlement. Okay, this is how important time factor is. Time factor T is equal to CBT HDR square. Okay, so this is the time expression for time factor. How time factor is related to the degree of consolidation here. So okay, can we solve same problems? Calculated the settlement calculation. Yeah, simple settlement calculation. All this thing. And then this time calculation, how much time is required, coefficient of consolidation calculation, CV. CV is the what? Is CV. This CV is the coefficient of consolidation. This how can we cancel? So CV is a material property, right? Soil property, type of soil. It depends upon the permeability of the soil and the coefficient of volume compressibility. Okay, that is a material property. CV, coefficient of consolidation. So how to calculate the CV, all those things. Things we did. Ah, CV calculation, all those things. Yeah, so see this, we are not going, so we don't have much time. Yeah, then we started the main topic of shear strength. So what is shear strength? Shear strength of soil mass is the internal resistance per unit area that the soil mass can offer to resist failure and sliding along any plane. Okay, so it's nothing but a resistance to failure, resistance to sliding along any layer. Okay, so in which layer? So if the soil mass, the soil will slide or soil will fail along the weakest plane. Okay, so at the in which that plane where you have the least resistance, shear resistance. Okay, that will be my always my failure plane. When you have the Moore Coulomb failure criteria, the material fails because of a critical combination of normal stress and shear stress, and not from either maximum normal stress or maximum shear stress alone. So this is very important. Always comes at a critical combination of shear stress and normal stress. So from this logic, we can get one envelope known as the Moore-Coulomb failure envelope. Okay, this envelope that is known as the Moore-Coulomb failure envelope. This is this uh, curved line. Okay, where you have this in one axis you have the shear stress and the other axis you have the normal stress. So in below this layer, it's the soil can sustain. At this layer means it is at the verge of it is at failure, and above this line we cannot have any stress state. Okay, the soil will fail before going to the stress state. Now this failure criteria can be represented as a linear function of linear function like this using the Coulomb's theory. The shear stress equal to C plus sigma tan phi. So this is known as the Moore-Coulomb failure criteria, and this line is known as the Moore-Coulomb failure envelope. Okay, so this was okay understood, right? So combining with the Coulomb theory, we get this sigma f is equal to C plus sigma tan phi. So this was actually got from this friction theory, right? So this frictional resistance of any sliding block can be represented normal stress times the what normal stress times the friction coefficient of friction that will give you the frictional resistance, frictional force, normal force times the mu is the uh, coefficient of friction is nothing but the tan of the angle, tan times the angle of repose, okay, or 10 times the angle of phi. Phi is nothing but the angle that is, if you drop the sand from the top, if you drop sand from the top, it will take a heap. You will take a triangular arrangement, right? The angle that the slope of the sand will make, that is nothing but the angle of repose or nothing but the angle of internal friction of that sand. So that is phi. So C plus sigma tan phi. C is the cohesion of the soil and phi is the normal stress, and y is the normal stress, and sigma is the normal stress, and phi is the angle of internal friction. So all those things we saw. She has a basic concept. We saw the direct shear test. We saw this ultimate shear strength. Fixed and loose sand will always behave like this. This is the critical state strength, and then you have the dense, you have the peak, and it comes ultimate strength, and you have the critical state strength for the dense one. So loose sand and normally consolidated clays behave similarly, and over consolidated clays and dense sand behave similarly. Yes, and then all this, and then we saw the triaxial test, CED, CU test. Okay, so you saw UU test results, then you saw the CU test results for normally consolidated clays. Always remember that my cohesion is zero. Okay, cohesion is zero. All right, and for over consolidated clays, you will have some cohesion as well as spike. Normally consolidated clays, cohesion is always zero. Okay. Now, these are the some of the problems that we solve. It's very easy, quite easy, nothing much to discuss. Directly related to the shear stress, due to the triaxial test, and also basic equation. This you have to remember. Sigma 1 is equal to sigma 3 10 square 45 plus 5 by 2 plus 2 IC 10 45 plus 5 by 2. This you have to remember. Others, everything is related to that itself. Okay. Then we saw the port pressure parameters, the B parameter, the A parameter. The B parameter is related to the first stage, okay, where we apply the sigma 3 cell pressure, in the cell pressure with application of cell pressure, how much increase in uh, pore water pressure is happening, that is given by B. If the B is very near to 1, that means the soil is almost completely saturated. So by measuring the parameter B, you can check before starting your triaxial test, that whether your soil is perfectly saturated or not. Okay. C test, C parameter, then you have the A parameter. C parameter relates the increase in pore water pressure to the increase in deviatory stress, that is in the second stage, in the sharing state of the triaxial test. All those things we saw. That we derived the stress path you saw, the PQ plots you saw. Okay. Stress path is a locus of points representing the stress stage during the progressivity. There is nothing but a stress path. Okay. Fine. Okay, so here you can see if you plot the stress paths, the at failure point, whatever stress path points you will get from the P and Q, those lines if you join, you will get one more line. Okay, this is the failure envelope, this is the more column failure envelope, and this is my line that I have got from the stress path. Understood, right? So that from that also we can calculate the C and phi values. Okay, so we are not just we'll not go into this in detail now. Just do it. I hope you have understood these things. Okay, this was how we derived the A and B, all those stuff. That's all. Then we solved some problems. Then what was the next topic? Next topic was the earth pressure. Okay, so active earth pressure, passive earth pressure is pressed. So in active earth pressure, the so wall moves away from the backfill. In passive earth pressure, wall moves towards the backfill, and in rest there is no movement of the wall. So in all these three cases, the soil mass is creating some amount of pressure on the wall, different amount of pressure on the wall. So that pressures we can calculate from the Rankine's earth pressure theory. Okay, Rankine earth pressure theory or the Coulomb earth pressure theory. So initially Rankine gave some theory where he considered that the wall to be frictionless. Then we considered the frictional wall that was given by Coulomb, and we also considered the inclined backfill and all those things we saw. Okay, then for dry submerged, partial submerged conditions, how to calculate the effective active earth pressure, passive earth pressure, all those things. See, all those we saw. Then we saw what C5 soil. C5 soil, how to calculate the earth pressures also. Those things also we saw, right? So there are twice C root over Ka, that term comes, or twice C root over Kp, that term comes. Right, in case of C5 soil. And also one thing that you should remember, second. This case, when tensile cracks develop and when tensile cracks do not develop, and the depth at which the tensile cracks develop, and all those things, these concepts you should be able to recall. Okay. Okay, this n phi is what? 10 square 45 plus 5 by 2. So 1 by n phi is 10 square minus 45 plus 5 by 2. Okay, that's all. That's the difference. So this is the active case, this is the passive case, this is why we look at 10 square plus 45 plus 5 by 2. And the inclination you should remember, So passive is inclined at 45 minus 5 by 2 and active is inclined at 45 plus 5 by 2. Okay, this failure wedge. So then we solve some problems regarding this, right? And this problems we solve. And this last three classes we have been solving these problems only, right? Many problems we solve from this earth pressure theories. Also many problems we solve from our this what to say, this other topic, this stresses in soil. Stresses in soils, that also is also we solve many problems from the earth pressure theories. Then we also solve problems from the stresses stresses at any point below the soil, that also we solve, right? To some loading, how much stresses will come, that problems we solve, those problems also we solve. Okay, so this was all, right? So that's all. This was all for this course. If you have any doubt, please feel free to contact me. Okay, thank you so much for attending this course, and I hope you prepare well for the exams and you have all of you actually perform brilliantly in the exam. And I'm sure that all of you will be doing very well because you have solved a lot of problems, we discussed a lot of things, and all of this should be clear to you by now. All right. So yeah, just solve more and more problems. Make keep your concepts clear always. Okay, don't confused between things. Don't get confused between things. Read textbooks. Without there is no substitute of reading a proper textbook. So as I suggest always that please go through standard textbooks. Read, if you finish reading one textbook, go to another textbook. Read one more textbook by some other author. So keep on reading. Okay, that is very important. If you will see that every time you read something, you will uh, you will get to know more and more about the things. Okay. So I will suggest you that, and please feel free to contact me if you have any doubts before your exam. So do not worry. So stay safe, stay healthy. Thank you so much for attending this course. It was a pleasure to conduct this live detective sessions for you throughout this 12 weeks and these 13 sessions, 26 hours. So thanks a lot for attending. Have a great exam ahead, great day ahead, and also have a great year ahead. So thank you, and good night. Take care. Bye bye.